Unit 6 has us extending our ideas in geometry into a unit on quadrilaterals. By definition, a quadrilateral has 4 sides, and the sum of the interior angles will always be equal to 360. So that's just a basic definition of a quadrilateral. When the quadrilateral starts becoming more specific, then we start talking about the properties that it exhibits, and we start to give them names. So the first topic we're going to talk about, the first kind of quadrilateral, is going to be a trapezoid. And if we are told that we have to prove that a shape is a trapezoid, we have to show that one pair of opposite sides is parallel to each other. So when you start to think about this, that should make sense. That we did the units previously on parallel lines, because if we have to make one pair of opposite sides parallel, we're going to need to use some of those same ideas. So in this case, let's suppose this is quadrilateral ABCD. If I could get line segment AB parallel to line segment DC, then I could show that ABCD is a trapezoid. So that's my role, is to show that one pair of opposite sides are parallel. Now, if we want that trapezoid to be also shown to be an isosceles trapezoid, we're going to notice that what it says is, in step 1, you have to make sure that it's a trapezoid first, which means you have to do the above. And then you have to pick one of these 3 ways to show that it's isosceles. So it can't be an isosceles trapezoid until it's first a trapezoid. Step 1, make it a trapezoid. Step 2, pick one of the 3 ways to make it isosceles. So back in middle school, you learned about the parts of an isosceles trapezoid. The parallel sides are called the bases, base 1 and base 2. The 2 sides that are congruent to each other are called the legs. So I'll just make this leg 1 and leg 2. They're not normally called leg 1 and leg 2, but we'll talk about it that way. And then the other thing is that there are base angles. Base angles here actually give us 2 sets of them, because we have a base 1 on top with a pair of base angles sitting on it. And we also have base 2 on the bottom with a pair of base angles sitting on it. And we want to consider them as base angle pairs. The blue ones are a pair and the pink ones are a pair. So when we go back and look about how we're going to make this trapezoid be isosceles, we see that one of the things that it says that we can do is we can show that the non-parallel sides are congruent. In our trapezoid here, let's suppose it's called E, F, G, H, we would have to show that EH is congruent to FG. Line segment EH congruent to line segment FG. If we were going to show the base angles congruent, which is the second way to prove that we have an isosceles trapezoid, the base angles congruent would mean that we either have to get angle E congruent to angle F, or we have to get angle H congruent to angle G. And then the last way to prove that we have an isosceles trapezoid is if we draw the diagonals in. If we can show that the diagonals in the trapezoid are congruent, we can say that it must be isosceles. So that's another way. So if we could show that line segment EG, that diagonal, is congruent to line segment FH, that diagonal, we would be able to classify this trapezoid as being isosceles. So at the top, how to prove that you have a trapezoid, followed by how to prove that your shape is an isosceles trapezoid. So that's when the final part of your proof, or somewhere in the proof, you have to identify that your shape is a trapezoid. I'm going to mention to you that the next section flips around your thinking. This is if you're told in your proof that you have an isosceles trapezoid. That would be like them saying, given your trapezoid is isosceles. And you'll notice here that the same 3 things that are here are the same 3 things up above. In this case, though, if your trapezoid is isosceles, you can actually pick any of these to use. because it's an isosceles trapezoid, any of those properties hold true. Up here, we only want to pick one to show that it's isosceles. We don't want to do that three ways. We want to just pick one of those ways. And the way that you're going to determine that is going to be based on which piece of information you can come to a conclusion to in your proof. So let's take a look at question number one. Question number one is talking about us making the shape a trapezoid. So when I say making the shape a trapezoid, you'll notice that it says A, B, C, D. They want us to make this shape here a trapezoid. So one of the things I try to look for is where that shape is. So I can see clearly what they want me to make a trapezoid. I also am pretty sure that to make the lines parallel, those are probably going to be the lines that are parallel just based on the way the picture is drawn. So it's kind of helpful to take a look at that shape. And when I go to look at my given information, it says that angle EBA is congruent to angle BCD. So those are the two angles that are congruent to each other. Remember, if I have to prove it's a trapezoid, I need one pair of opposite sides parallel. And when I take a look at what I have in this picture, I see an F shape with those two angles. So what I can say then is that I know that AB must be parallel to DC line segments, because if corresponding angles are congruent, lines are parallel. And we know that any angles that fall on the F shape, the angles that fall in the little pocket of the F, are corresponding angles. So we were just able to use those corresponding angles to force these lines to be parallel. You may not notice this, but we're actually at the last line in the proof, because up above, you know that if you have to prove that ABCD or any quadrilateral is a trapezoid, you need one pair of opposite sides parallel, and I just did that here. So I can say if one pair of opposite sides is parallel, the quadrilateral shape that we're working with is a trapezoid. So we have basically one way to make it a trapezoid, and they gave us the angles that allowed us to do that. So I am now done with that proof. As I continue on to the next proof, in this next proof, it says that we're supposed to make this an isosceles trapezoid. So I'm going to give you a little reminder that it can't be isosceles until step one, it's just a plain trapezoid. So it has to be a trapezoid before you can make it an isosceles one. So I'm going to take a look at the information that they're giving me here. And one of the things that they're giving me is angle DCB is a supplement to angle CBA. So back in the unit on parallel lines, we talked about what happens when these angles, which is sort of what I have right here, if you want to look at it that way, when those angles are supplementary. Those angles that you see there can be called one of two different things. They can either be called consecutive interior angles, or they can be called same side interior angles. I've seen both. And the rule is that if they are supplementary, it means that the lines are parallel. So if I go back and I take a look at what I have in my picture, I've got these supplements here, which is going to mean that these lines are parallel. So when I put that into my proof, I'm going to put that DC, line segment DC, is parallel to, and I'm actually just going to call it EAB here. You could just call it EA, that line segment, or line segment AB, or line segment EB. I'm just going to use three letters just as a reminder to you that if you ever see that, you know that that means that it's a straight line that goes from E to A to B. And I'm going to say here, if consecutive interior angles are supplementary, lines are parallel. And that is one of the things that we did talk about way back when we did parallel lines. We just don't use it much, so it doesn't show up very often, but it is good to know. Which also means that if I'm trying to make my shape be an isosceles trapezoid, that what I have just done is I've shown that these opposite sides are parallel, which means that this shape that they're talking about, which lands in here, has one pair of opposite sides parallel. As soon as I get that one pair of opposite sides parallel, I can say that BCDE is a trapezoid. First step, make it a trapezoid. Number 3, if one pair of opposite sides is parallel, the quadrilateral is a trapezoid. So I've met the first condition. I made it a trapezoid. My next step is going to be to turn this trapezoid into one that's not just a plain old regular trapezoid, but it's instead an isosceles trapezoid. I have 3 ways to do that. The way that I'm going to determine that I'm going to use is going to be based on the given information. So I'm going to go in here now and I'm going to take a look at the given. And one of my givens says that angle E, which is allowed to be called angle E because there's only one angle E, and angle DAE are congruent to each other. And what we've talked about numerous times is every time they give you a piece of information, there has to be a reason why they gave that to you. So what I'm looking at is this little triangle called DEA, and I'm realizing that in that triangle they gave me these 2 angles congruent, which means that these 2 sides are congruent. So I'm going to put that these 2 sides are congruent to each other. So I have in here that DE, line segment DE, congruent to line segment DA, if 2 angles in one triangle are congruent, the opposite sides are congruent. I may not know exactly why it is that I'm doing that, but it is definitely something that's true based on the information that they gave me. When I move on to the next piece of given information, one of the things that I notice in the next piece of given information is that I have 2 sides that are congruent to each other. That's DA and CB. And when I first look at that, I may not realize why they would give me that until in my brain I link together the fact that this has a DA and this has a DA, and if line segment CB is congruent to DA and line segment DE is congruent to line segment DA, then by transitive, line segment CB must be congruent to line segment DE. So I've got 1 link, 2 sets of congruence, that's transitive. So I have this congruent to this. In my shape, it's a trapezoid, it now has the non-parallel sides congruent, which allows me to say that not only is BCDE just a plain old trapezoid, it's now an isosceles trapezoid. The reason is if the non-parallel sides are congruent, the quadrilateral, actually I'm going to change that, the trapezoid, all right, the trapezoid is isosceles. And I've gotten to my final prove line. At this point, we're going to move on and we're going to look at some algebra type questions. More numerical, I guess, than algebraic. They do not give me a picture with either question 3 or question 4, so I'm in charge of drawing my own. And when I go to draw my own, I have to pay very close attention to the information that they give me. So they're a little particular here in the way that they want their picture drawn. So I have a trapezoid. It does not say it's isosceles, so when I draw it, I want to draw it looking very non-isosceles. The parallel sides are BC and AD. If I put BC here, I have to put A there and D here, because if the name of it is A, B, C, D, wherever A is, I have to be able to work my way around the picture alphabetically according to its name. And if I put it any other way, this won't work. So we have to be a little careful on how we draw it. It tells us that there is one diagonal from B to D that's drawn in. And it tells me that the measure of angle CDB is 50. CDB is 50. So this angle right here is 50. And it also tells me that angle ADB is 25. And it's actually asking me for the measure of angle C. So when we have this question, at first glance, you may say, well, geez, that's not really enough information to get me anywhere. Please remember that the parallel lines and the transversal form the Z shape, which means that I have alternate interior angles that are congruent to each other. So the angle in the upper left there is also 25. And then I can take this and focus my attention now on this triangle. 25 plus 50 gives me 75, so the triangle uses 75 degrees, which means the measure of angle C can be gotten by taking 180 and minusing the 75 from it, which is going to give me a final answer of 105. So I'm working my way around in the picture, filling in the missing measures, and remembering all of the details of things that we've done before. In question number 4, it does change now, and it tells us that it is an isosceles trapezoid. So like we've talked about before, that means I want to be a little careful on how I draw it. So I'm going to draw it so it looks kind of isosceles. Notice the parallel sides. AB, be careful, CD, because you have to work your way around the shape according to the way that they name it. And it does say in here that we have some diagonals. Actually, just one diagonal BD is drawn. And the measure of angle C is 80. So some of you may say, well, geez, that's no big deal, that's 80. I consider that to be a pretty big deal because that also means that this angle is 80 because this is another base angle. So this whole entire angle is 80. Base angles are congruent. When they move on to the next piece of information and they tell me that angle DBC is 35, that allows me to put my focus on this triangle that's in here, and I will know that the missing angle that's over here will be whatever I get when I subtract the 115 for the degrees that are used in that from 180 and end up with 55. How about 45? So I end up getting 45. So this little angle that's right here is 45 degrees. I go back now and I take a look at the whole entire image of what it is that's going on here. One of the things that I do know is that because this whole angle is 80, if I just used 45 for the little stretch here, then that means that this is 35, because 35 plus 45 equals 80. The other thing that I know is that I have a Z shape in here. And if there's 45 degrees there, then there's 45 degrees here. This final question is asking me to find how big angle A is. And angle A is in a triangle that uses a 35-degree angle and a 45-degree angle to give me 80. 180 minus the 80 that's used leaves me with the measure of angle A equaling 100 degrees. So this has to be 100 right here. There are other ways to do both of these questions. That's just the way, while I was doing it this time, that I happened to notice how to fill them in. You may have taken a different route and gotten the same answer. The last piece of information that we need to talk about today is what happens when we have a median and a trapezoid. Median in a triangle, we know, connects midpoints, a vertex to a midpoint. In this particular case, the median connects midpoints of two sides. So the two legs in this triangle get connected midpoint to midpoint, and we end up having what we call a median. Sometimes it's called the mid-segment, but more often I see it called the median. So in order to go through and answer these questions, there's a rule. And the rule says that basically the length of the median is equal to the average of the length of the bases. I think if you're looking at that, that can be a little bit confusing, so I'm going to write a formula for you. I'm going to tell you that the median is equal to base 1 plus base 2 divided by 2. And you should feel comfortable with that formula because previously in math you had a formula for the area of a trapezoid, 1/2 times height times base 1 plus base 2. So this is still using that base 1 plus base 2 that you're already comfortable with. So in here, if I use that formula that the median is equal to base 1 plus base 2 divided by 2, the median in this one is labeled as x. Base 1 is 21 on top. Base 2 is 11 on bottom. And I'm going to add them and divide by 2. So that's 32 divided by 2, which means my median, which is labeled as an x, turns out to be 16. Sometimes question 6 can be a little bit confusing. Please remember that your median is 18 in this case, base 1, base 2. Base 1 is x, base 2 is 30. So when I plug into this same formula, I'm not going to plug in the same way I did on the last question. The median in this case is 18. Base 1 we don't know. Base 2 is 30. And the formula says, whoopsie, that you add them and divide by 2. So I add them and divide by 2. I'm putting the 18 over 1 so that I can cross multiply. The reason why we cross multiply, 18 times 2 gives us 36, is because when I cross multiply, I get rid of the fraction. And when I solve, I find out that x is 6. So when I get an x value of 6, technically what that means is however big of a difference there is between the 6 and the 18, which is 12, is how big of a difference there needs to be between the 18 and the 30, which is also 12. So there's a quick little common sense way to sort of check that answer and know that what you did is right. Question 7 is a little bit more involved because of the algebra only. So when we go through and we do this, we just want to make sure that we're still substituting in the same exact way. The median, 3x minus 1, equals the top base, x plus 12, plus the bottom base, also known as base 1 and base 2, divided by 2. So I'm going to do the same thing we did on the other ones. I'm going to put that over 1 so there's a fraction on both sides. And on the diagonal here, I'm doing 2 times 3x minus 1 equals, and I'm going to combine like terms and get 4x plus 14 times 1. Distribute. Minus the 4x from both sides, add the 2 to both sides, and I end up getting an x value of 8. I have seen this question where they ask you to go back and say substitute in here and find the length of AB or the length of DC or something, but in this case the directions were just telling us to find x. And remember, this rule only works when your median is connecting midpoint of one leg to midpoint of the other.